Hey physicists, today we're going to talk about vector cross products, and to give you a little bit of history, in the fall, if you remember, we talked about a vector dot product. And a dot product is when you have two vectors, like maybe force, which has a direction, and displacement, which has a direction, and you multiply those two together and you get a third value, but that value is a scalar value. It does not have a direction. So when I take force times displacement, I get energy, which is work. And that's a scalar value. Now, shouldn't it make sense that if I could take two vectors, multiply them together, and get a scalar value, I could also take two vectors and multiply them together and get a vector value? And that's really what your vector cross product is. It's when you multiply two vectors together to get a third vector. So maybe I have this vector A, which goes in this direction, AX, AY, AZ. I have vector B, which goes in this direction, BX, BY, BZ. Then whenever I draw C, C has to be perpendicular to A and to B. So C must be going up in that direction. And the way that I would find it is by doing this A cross B. To find the values of the I, J, and K, or the X, Y, Z values of C, we're going to set up a matrix here where I have my I, J, K, or X, Y, and Z. I have AX, AY, AZ, BX, BY, BZ. Now, I'm going to extend my matrix off to the sides here. You'll see why once we get going, but I want to follow the pattern. So I have AX, AY, AZ. Then my next number here is going to be AX. If I work my pattern backwards, AZ, AY, AX, then AZ is going to be my next number that goes on the left side. I'm going to do the same thing with the B, so I'm going to have X, Y, Z, X, Y, and working backwards, Z, Y, X, Z, Y. And if I cross to the right, it'll be a positive value. If I cross to the left, it will be a negative value, and that'll make sense here in a second. So when I cross to the right, I'm going to have AY times BZ, positive. And if I cross to the left, I'm going to have AZ times BY, negative. Then I'm going to do the same thing for the J value, AZ times BX, AX times BZ, and the negative goes with the one that's crossing left. And then again, for my K value, I'm going to have AX, BY minus AYBX, and that's how I would find the values of the X, Y, and Z of that C vector. Notice too, one observation, that when I'm looking at the X value of the C vector, it does not include either A or B's X component. It is only the Y and the Z component. And notice too that those two components flip-flop. So I have AY first, but then in the second part I have AZ. And then the first one I have BZ, and the second one I have BY. Same thing when I'm looking at my J, there's no Y component of the A and B. And when I'm looking at the K, there is no Z component of the A and B. So the next thing we would look at then is the magnitude, which is the area of the parallelogram, is the magnitude of the C. So when I look at this Pythagorean theorem to find the value of this, that's what your absolute value is. It strips it of the positive and negative, but what really is a positive negative? It's a direction. So it strips it of the direction, and the way we would do that is just to do cx squared plus cy squared plus cz squared, square root that, and that gives us a value. Now, if I look over here in the picture, I could take and extend this, creates this parallelogram here. Well, the C value, or the length of the C vector, is really the area of that parallelogram, okay? So if B and A are perpendicular to each other, then C is just these two times each other, right? Think of this as maybe being a rectangle. The area of that rectangle is the length times the width, or A times B. If they are not perpendicular to each other, the area of the parallelogram is AB sine theta, where theta is this angle here that is between A and B, the angle between A and B. Now, to find the direction, we would have to use what we call the first right-hand rule. And for some of you, you just had seizures because that takes you back to when we studied magnetic forces, magnetic fields. So I shoot a particle into a magnetic field. What direction is the force acting on the particle? Well, that was really a vector cross product. We just didn't call it that at the time. So we're going to take our hand, and what we did then was we said our fingers go in the direction of one vector, our thumb goes in the direction of another vector, and our palm goes in the direction of the third vector. That's the picture on the left. You'll often also see this like this, where you have your thumb one way, your pointer finger one way, and your middle finger another way. That also gives you like the XYZ axis. That's a really common way of doing the right-hand rule also. So again, we did that with magnetic fields and forces on a particle. So sample problem, I have this vector p, which has 4, 0, 0, so it's only on the x-axis and 4. Then I have vector q, which is only on the y-axis, 0, 3, 0, and I want to find the cross product. I want to find the magnitude of r, and I want to prove that the angle between them is 90. So there are a couple different logic things we can do here. So if the resultant of this, or the cross product, is the area of the PQ rectangle, then since this is on the x, this is on the y, then isn't that area really just going to be 4 times 3, which will be 12? So our answer should come out to be 12, right? And if this is all on the x, this is all on the y, then shouldn't my answer all be on the z, showing that these are perpendicular, that C has to be perpendicular to A and B. And then also, can't we prove using this guy that the angle between A and B is 90 degrees? So that's where we're going with this. Okay, so the first thing we're going to do is we want to find the IJK of that cross product. We're going to set up a matrix, so IJK, or you could do XYZ, 4, 0, 0, 0, 3, 0, and again, we're going to extend to the side following our pattern. So 4, 0, 0, 4, and if I work backwards, 0, 0, 4, 0. Same thing for the bottom row there, 0, 3, 0, 3, 0, 3, 0, 3, 0, 0, 3. And now I can cross. So I'm going to take 0 times 0 gives me 0, 0 times 3 gives me 0, and I'm on the right track because that means nothing is in the x direction. Then I'm going to take 0 times 0, which is 0, times or minus 0 times 4, which is 0. Then I'm still on the right track. Nothing is in the y-axis. Then I'm going to take 4 times 3, which is 12, minus 0. And there we just showed that it's 0, 0, 12, that the cross product is perpendicular to A and B. Now, how would I find the magnitude of this? We can obviously look at that and say that, well, the magnitude is 12 because these two are zeros, right? Or we could use this Pythagorean theorem and say the square root of 0 squared plus 0 squared plus 12 squared gives us 12, and that's got to be the magnitude of that cross product, or of the resultant. So prove that the angle between P and Q is 90 degrees then I can take and put that 12 on the left side, following this over here, the C magnitude of C is equal to the magnitude of A times the magnitude of B times the sine of theta. So to find the magnitude of A, I'm going to take the square root of 4 squared plus these zeros that go away. Then I'm going to take the magnitude of the Q, which is the square root of 3 squared, because the zeros are going to go away. So I end up with 4 times 3, which is 12. Divide the 12 over and get 1. So 1 equals the sine of theta. Well, when the sine of theta is 1, what does theta got to be? Theta has to be 90 degrees. So we just proved that A and B are 90 degrees to each other. Then when have we already studied this, where we have 3 vectors that all 3 of them are perpendicular to each other, or the cross product, which you didn't really know was a cross product at the time, is really the product of 2 vectors that are multiplying together, and that's going to be when we studied torque. We said that torque is a force times a radius. So I have my force this way, my radius this way, and then the torque is out of the object. So if I'm pushing this way, then it's either going to be towards me or towards the screen there. That's the direction that the torque would have. And then that's what we studied previously. Now the next thing we'll study that has that is angular momentum, where we'll talk about the angular momentum of an object, and it will also be a vector cross product. So here's a U-try problem. So we would have the radius of 5, negative 2, and 7, and a force that is 9, 1, and negative 3. So find the torque, which is the cross product of that radius and that force. What is the magnitude then of the cross product? And then what is the angle between R and F? So take a moment and pause the video, and then I'll give you the solution. So here you go. The torque is going to be negative 1, 78, and 23. The value of the torque is going to be the Pythagorean theorem of those 3 numbers, which gives you 81.3. And then whenever you do this equation that we did over here with the sine value, then we get our theta value between the radius and the force to be 74.8 degrees. So in summary, remember that when you multiply 2 vectors together and you get another vector, that is a vector cross product. And that third vector, the C vector, is perpendicular to the first 2 vectors. The magnitude of that is really the area of that parallelogram. We would calculate that by setting up our matrix and doing the crosses from the matrix, and then the Pythagorean theorem of our I, J, and K values. And then the direction for that, we would use the fingers, thumb, and palm, which is the first right-hand rule, either fingers fingers, thumb, and palm, or we would use, sometimes you see it as this way, where you have your thumb, your pointer, and your index finger or your middle finger going different directions. So that's your X, Y, and Z axis from that. And that, in a nutshell, is vector cross products.